In this video, we're going over the concepts for Lab 7, which is titled Phet Molarity Activity. The goals of this experiment is that students will be able to calculate the molarity of a solution, and students will recognize how changes to the amount of solute affect the molarity of a solution. We are first going to discuss what is the definition of a solution. And a solution is another word for a homogeneous mixture. Remember that these types of mixtures have a uniform composition and they have the same properties. But when we're talking about in terms of a solution, we're going to say that a solution is composed of two things. Number one, a solvent, which is going to be the substance that is present in a larger amount. And in a solution, we have one solvent. Solutions are also composed of solutes, and it can have one or more solutes. And those solutes are going to be the substance or substances that are present in lower amount. Here in the slide, we have the example of whole blood. We know that blood is composed of plasma, is composed of platelets, white blood cells, red blood cells. So if whole blood, which is a homogeneous mixture, undergoes a process of centrifugation, which just means that it's going to be spun really fast, we can see that the components then illustrate what is the percent on average that each of them represent in our homogeneous mixture. So we can observe that the majority of blood is plasma at about 55%. So that is the major solvent found in blood. The white blood cells, the platelets, and the red blood cells are going to be the solutes present in this mixture of whole blood. Next, we need to understand how is it that we talked about the concentration of solutions. Molarity is one of the ways in which we can talk about the concentration of a particular solution. Specifically, molarity measures how many moles of solutes it dissolves in 1 liter of solution. If 1 liter is the volume of the solution. But understand that in general, when we're talking about molarity, the units are moles per liter. And that's what you see in the following equation. Here in the bottom right side of the slide, we have an example of making a cobalt 2 chloride dihydrate solution in ethanol. And it is done in the following way. First, you're going to measure the amount of solute. And as you can see in the top loading balance, 10.0 grams of cobalt 2 chloride dihydrate have been measured. In this example, we're trying to make a 500 milliliter solution of that cobalt 2 chloride dihydrate. So if it's placed in a volumetric flask, at first we're going to add some solvent, which is the ethanol. Remember, the cobalt 2 chloride dihydrate, that is going to be our solute. And then that mixture is going to be swirled until the solute is dissolved. Then additional solvent is added up to the mark of the volumetric flask, which is the device that is being utilized to measure volume. And that's how we made the solution. But as you can see in this problem, this is just illustrating how to prepare a solution, but it's not telling us what is the concentration of the solution. But the information in order for us to calculate the molarity of the solution has been given overall. So from the problem, we can see that we have the volume of the solution. And the volume of the solution is 500 milliliters. Remember that when we're calculating molarity, we need to have those milliliters be converted to liters. So 500 milliliters is equivalent to 0.5 liters of volume. The other piece of information that we need is the moles of solute. We know that when it comes to the solute, Specifically, in the top loading balance, 10.0 grams of that solute was given. But understand that when we're calculating molarity, we need units of moles. So, in order to get the moles of the solute, what we're going to do is take into account that 10.0 grams of the solute. If we take that and use the conversion factor of molar mass, we know that the molar mass given the chemical formula for this cobalt 2 chloride dihydrate is 165.8698 grams. That is going to equal to 1 mole of the solute. Let me just highlight the solute so we keep track of this. So that number is because that is the molar mass of the solute. So by taking the amount of solute that was measured in the top loading balance, and we divide it by the molar mass, so 10.0 divided by 165.8698, we can determine how many moles were actually measured. And in the case of our solute in this example is 0.0603 moles of solute. So now that we have the moles of the solute and what is going to be the volume of our solution in liters, to find the molarity of this particular solution, we're going to take these moles and we divide it by the volume. And then we round it to one significant figure. We can see that the molarity of the solution that is illustrated in this image is 0.1 molar. Now, in other problems, if you are given just the moles of solute and the volume of the solution, because they have the correct unit, you can go ahead and divide them, which is the problem that we have in the next page. If we're trying to determine the molarity of a solution, if you have 3.0 moles of solute and is dissolved in 12 liters of the solution, here, because the solutes already have the correct unit and the volume is given in the correct unit, you can put it directly into your equation. So molarity equals 3.0 moles of solute divided by the volume of the solution, which is 12.0 liters. This solution specifically has a molarity of 0.25 molar. So now you see the procedure for when you measure the grams of a particular solute and you know the volume overall of the solution, how to calculate molarity, versus if you're given the moles of the solute and the volume in liters of the solution, this is the way how you do those calculations. When it comes to solutions, understand that solutions come in different types. Solutions can be unsaturated, saturated, or supersaturated. The difference is of how much solute is going to dissolve after that solution has been prepared. In the case of an unsaturated solution, because that solution has less than the maximum amount of solute that can be held by the solvent, more solute is able to dissolve. In the case of a saturated solution, because that solvent has the maximum amount of solvent that can hold, no more solute is going to dissolve. And at times in saturated solutions, we see some of the solute in the bottom. Supersaturated solutions, on the other hand, are going to be solutions that have more than the maximum amount of solute that can be held by the solvent, and you utilize things like temperature in order to create them, but understand that they are unstable, and if you add specifically more of that solute, it's going to start forming crystals because of the process of nucleation. Another important concept that we need to understand when it comes to solution is dilutions. And dilution occurs when the volume of the solvent in a solution is increased. Let's say that we have a particular concentrated solution. And we understand that this solution is concentrated because we can see that it has a dark color. When we look at the molecular level of a concentrated solution, we see that when it comes to the amount of solvent and solute, we see a lot of solute in a small amount of solvent. Upon dilution, what we see is that concentrated color is going to become lighter, because remember, we're increasing the volume of the solvent. And when we look at it at the molecular level, we see that there's a small amount of solute in a larger amount of solvent. And that means that our solution has been diluted. When it comes to dilutions, we have the dilution equation. In the dilution equation, as you can see, is M1 times V1 equals M2 times V2, in which M1 is the initial molarity, meaning the stock solution that we have, meaning the concentrated one, and then the initial volume that we're going to take from that stock solution in order to make the diluted one. So M2 is the final, meaning the desired molarity that we're trying to make. And V2 is the final volume that we have specifically in liters. Understand that as long as the volumes match in V1 and V2, liters is not required. Those volumes can be also be in milliliters, okay? But basically V1 and V2 have to match in terms of units. So V1 and V2 must be both milliliters or both liters to be utilized in this equation. Now we're going to proceed to do a dilution problem. In this dilution example, the problem reads as follows. How many milliliters of a 2.05 molar NaOH solution are required to make 525 milliliters of a 0.150 molar NaOH solution? So, what is given in this problem is M1, which is the stock solution, the concentrated one, which is 2.50 molar, and we're talking about NaOH. We are trying to find V1 because the problem is saying how much do we need of that stock solution to make a new volume with a new concentration. The final volume that we're trying to do is 525 milliliters. That is the desired volume of our solution. And M2 is going to be the desired concentration that we want, which is 0.150 molar of NaOH. So utilizing the dilution equation, I can calculate my V1, how much of that my stock solution I need. So because I'm solving for V1, I can rearrange this equation, and it's going to be M2 times V2 divided by M1 is what's going to give me that V1 term. All I'm doing overall, let me use a different color, is that I'm dividing both sides by M1 to cancel that M1 term and leave by itself that V1 term. So now that I have rearranged my equation, V1 equals M2 times V2, everything divided by M1. I put in the values, which is 0.150 molar, and that's of NaOH. And I'm going to multiply that by 525 milliliters. I'm going to divide all of that by 2.50 molar of NaOH. When it comes to units, the molarity is going to cancel. So my units are going to be in milliliters. So when I take 0.150 times 525 divided by 2.50, that equals 31.5 milliliters. So what does this mean? If I try to illustrate it, let's say that I illustrate it utilizing a graduated cylinder. If this is 525 milliliter marking, and this is 31.5 milliliters, what the problem is stating, and I'm just going to utilize this lavender color for the NaOH, is that this 31.5 have been added to my container, and that's my NaOH, and then I filled the volume up to 525 with my solvent, which for NaOH most likely is water. So overall, how I made this solution is that I took 31.5 milliliters of that NaOH solution that started at 2.50 molar, and I added to it. So if I take my V2 minus my V1, I added to it 493.5 milliliters of water in order to make this solution. For this lab, be very careful when you're answering the questions, because if you are trying to calculate how much volume of the solvent it's needed in order to make a particular solution, remember that I obtained this number by saying V2, which is the final volume of the solution, I'm going to subtract from V1, which is how much I added of the stock solution. And that tells you how much solvent was added to make a particular solution. When it comes to the experimental procedure for this lab, understand that this is going to be in a new virtual lab platform, which is called Phet. In the lab on page 3, we have two different links that is going to allow you to reach the simulation. When you click any of these two, or you copy and paste any of these two addresses, you're going to be taken to the Phet platform, and this is how the simulation would look like. Overall, the lab is made out of 4 parts. Part A is just showing you specifically just the different parts of the simulation itself. Where you're going to do actual work is going to be in part B, C, and D. In part B, you're going to explore the effect of changing the amount of solute and solvent. In part C, you're going to do some calculations and you're going to be predicting the concentration of a diluted solution. So for part B and C, you will be using the simulation. And then on part D specifically is going to be just more practice for dilution equations. For part D, you're not going to be using the simulation. Make sure that you check in the lab sheet for all the instructions. And in the next video, you will see specifically illustrated part A and part B to know how to work with the Phet simulation for molarity.